All right, we're going to look at uniform circular motions. We're just going to get our toes wet here in circular motion. So we're going to zero in on uniform circular motion. So this is when the object's moving at a constant speed, not constant velocity, constant speed, around in a circle. Now this could be anything like, for instance, you standing on the surface of the earth, you are moving in a constant circle. Okay? We could talk about a car driving around a roundabout. Okay? But we could also talk about instantaneous points. So you could think about a plane making a dive and then circling up. Now at this point, they are on part of a circle. And so I could think about this point right here as being somewhat of circular motion at an instant. So we can use these equations, or some of these equations, I guess, especially this first one, to talk about instantaneous circular motion. All right, so let's talk about what these equations are telling us. The first one is telling us that the magnitude, so not the direction, they haven't told us anything about the direction, of the centripetal acceleration is equal to the speed squared over r. R here stands for the distance from the object, or whatever it is that I'm finding the acceleration for, to the axis of rotation. Okay? Not the radius necessarily, but a distance from an axis of rotation to my point. We can also talk about these two. These two are more meant for uniform circular motion, where something might travel at a speed. They'll go a distance, which is 2 pi r, the circumference, in a time capital T. The capital T stands for the period, which is defined as the time to go around once. We also have frequency, which is kind of the inverse, or is the inverse, of period. So I might talk about something having a period of 2 seconds. So it has a frequency of a half a second. So every half a second, it will complete one loop. I'm sorry, it completes half a loop every second for a frequency. Okay. Next, I want to talk about that R value a little bit more here. So if you were standing at the equator, here you are at the equator, your R value is from the center of the earth to there. So it is the radius of the earth. But if you're standing up here at the 45th parallel, your R value is this. From the axis of rotation perpendicularly out to you. And so when you get to the North Pole and you stand on the North Pole, your R value is 0. R is from the axis rotation perpendicular out to that object. Okay? The other thing is, this gives me the magnitude of the centripetal acceleration. The centripetal acceleration always points radially inward. The reason we need this is these two are perpendicular. Whenever your velocity and your acceleration are perpendicular, only the direction of the velocity is changing, not the magnitude. And so that means my speed will stay constant and I'll have this uniform circular motion. Think back to when we were in motion. If the acceleration and the velocity are in the same direction, speeding up. Opposite direction, slowing down. Even if it's like this, they're still kind of in the same direction, so it's still kind of speeding up, but it's also turning. Okay? When they're perpendicular, it's only turning. Okay? So in this case, this would be the center of this imaginary circle this fighter pilot was going through, and so that would be the direction of the centripetal acceleration. All right, so let's try a problem here. So I have a carousel, I have a person that's riding on it, and once every 12 seconds they make a loop. So if I'm standing on the side waving to them, taking the picture, every 12 seconds they will come by me. The distance from that horse they're riding on to the axis of rotation is 5.5 meters. And so I might say, well, what is the centripetal acceleration of that rider? Okay. So I think about what information I'm given. So when it says once every 12 seconds, they are telling me a period. Okay. If they told me 22 times per second, they would be telling me a frequency. And the distance from the axis of rotation, so this is my R value. So they've given me period, and they've given me R, and they want me to find AC. Okay, so in order to find the centripetal acceleration, I need to know the speed they're traveling at. Well, since it's uniform circular motion, I can use the speed is equal to the circumference divided by the time to go around once, which is 12 seconds. So I can figure out my speed by saying it's going to be 2 pi times 5.5 divided by 12. Okay. Then I need to plug that into my centripetal acceleration equation, which says that AC is equal to v squared over r. And in the end, I'll get a magnitude, but I want to get a direction. It's always going to be pointed radially inward. Okay. I can put these two equations together, these two right here, and what I'll end up with is I'll end up with something that's 4 pi squared r divided by t squared. And you might say, well, the 4 is 2 squared, pi squared, r isn't squared, t is squared. Why didn't the r get squared? Because I'm dividing by an r after I square it. So I have r squared divided by r just gives me an r. So in the end, I can plug all this information in, so I could type in just 4 pi squared times 5.5 divided by 12 squared. And you get something like 1.5 meters per second squared. Notice that it's an acceleration, so we're going to have units of meters per second squared. And it's going to be directed radially inward.